Hello everyone, welcome to my demo. I'll just be going over question number 6 on the May 2024 Physics GCSE Paper 1. In a ride at a theme park, a person is strapped into a pod that is attached to two stretched bungee cords. The bungee cords behave like springs, and figure 10 shows a person using the ride. Now, before the release, the bungee cords are both stretched. You can see the person is on the ground. After release, you can see that they reach some height above the ground. Now, question 6.1 asks, which energy store increases as the bungee cords are stretched? When the bungee cords are stretched, well, they've already given us a clue. They've said that the bungee cords behave like springs. When the bungee cords are stretched, they will have an elastic potential energy store. So you can even verify that yourself by taking a look at the system. At this stage right now, the person is effectively on the ground, so they don't have any gravitational potential energy stores right now. However, when they are released and they increase in height, they will do. Their energy will be converted into kinetic through movement, and then gravitational potential energy is what they will have at the end when they reach their maximum height, and they'll have zero kinetic energy. And all the elastic potential energy in these bungee cords will have been transferred into gravitational potential energy. So, which energy store increases as the bungee cords are stretched? That would be elastic potential energy. Now, moving on to the next part of this question, the calculation. When the pod is released, the pod accelerates upwards. Before the pod is released, the extension of each of the two bungee cords is 8 meters. The spring constant of each bungee cord is given, and so is the mass and the gravitational field strength. We need to calculate the maximum height reached by the pod using the physics equation sheet. So first of all, I would like you to notice that we are figuring out this maximum height, and so there are a couple equations that we should absolutely be using. For the first equation, we will need to use the elastic potential energy equation, which is, let's write it down, the elastic potential is equal to half k, so half times k times by E squared, where E is extension and k is the spring constant. So one of the most common mistakes that I see students making on these type of questions, especially these 6 markers that seem to be a bit more tricky to deal with, is that they make mistakes or forget on certain details. So in this example that they've given us, the detail that you can make a mistake on is simply substituting 8 for the extension and calling it a day. Well, we can't really do that because they've given us our clue here. They've told us that before the pod is released, the extension of each of the two bungee cords is 8 meters. Let's substitute all of our constants in and get our elastic potential energy for one bungee cord. So it's going to be equal to 12 times by a spring constant, which is 735, I believe. Yeah. Times by extension, which is 8 squared. Okay, so let's use our calculator to do this. We should use correct buttons and make sure to include brackets just in case. Times by 8 squared. And that gives us 23,520. But remember, we must times this by 2, since this is only for one bungee cord. So we times this answer by 2, and that yields 47,040. So let's write that down here. So for both, it's going to be equal to, just you can just do this calculation without doing the half as well, and it will give you that answer. So it's 47,040, I believe, joules. So the next part of this question is going to be to calculate the maximum height reached by the pod. Now, in order to do that, we need to understand what's actually going on here. So like we alluded to earlier, this elastic potential energy is going to be converted fully into gravitational potential at its maximum height, because there will be no kinetic energy, as it will not be moving at its maximum height. It moves, slows down, reaches its maximum height where it's not moving at all, and then it falls back down to the ground. Using this reasoning, we can state that this energy should be equal to the gravitational potential energy at max height. So therefore, the equation for gravitational potential energy, we can write down here, GP GPE is equal to mg delta h. And we essentially want to rearrange this equation for delta h, which will be our change in height. So let's do that first. Delta h is going to be equal to GPE divided by mg. Therefore, our change in height will be this 47,040 that we've been given, divided by our mass, which I believe was 240 times by gravitational acceleration, or gravitational field strength here, which is 9.8 newtons per kilogram. So let's do this on our calculator as well, substitute everything in and see what we get for our max height. So we can use the same button, answer, substitute this in, 240 times 9.8. And that yields an answer of 20, which is really reasonable. So let's look at that. 20, and that should be meters for SI units. 20 meters. So sometimes using common sense, you can sort of eliminate incorrect answers. If you're calculating that the speed of someone running down a track is, 700 miles per hour, you probably need to go check your working out. Okay, so now that we have this, let's take a look at the final question. Within this question number 6, the actual maximum height reached by the pod will be lower than the correct answer to question 6.2. We need to explain why. So let's go back to the actual diagram and see what's going on here. What we've done is we've assumed that all of the energy that's stored in the elastic potential energy stores of these stretch bungee cords is converted into gravitational potential energy. Now, this isn't what happens in reality. Any movement that happens in reality, it will not be 100% efficient for energy transfer. There will always be some energy wasted in some forms, because energy transfer in reality is not 100% efficient. It's fine. It's not 100% efficient, and some energy will be lost to the thermal energy stores of the surroundings, and then you can put in brackets through air resistance as pod moves upwards. So it's just giving a little bit of extra background to sort of secure our answer. But that is exactly why we have this theoretical maximum height. And our real maximum height, if you were to set up this experiment, you would observe that whatever you calculated, how high the pod actually goes, would be slightly less. And that would be, you could use that to calculate the energy that was wasted by friction. If you can just get that change in height, you can also just sub that into the same equation and find out how much energy has been lost due to resistive forces.